Well, hello everybody. Welcome to our discussion of section 2.2, where we will talk about the Gaussian elimination method or Gauss-Jordan method of solving a system. So this is solving systems of linear equations using Gauss-Jordan method, and also known, this method is also known as elementary row operations. Okay. So in this method, we will make use of the coefficients of the variables in a system. So let's make sure that you have this in your notes. Solve a system, and that initial matrix of the coefficients that we need and we create before starting the steps to solve the problem is called the augmented matrix. So I want to also put that in writing. The augmented matrix. Okay, so let's see how this works. We have, suppose, let's have a look at an example. Suppose we have this system. So we want to write the augmented matrix for this system, which is, let me move this up a little bit, which is 4x like that. So this is the system for which we want to write the augmented matrix, and that'll be just the coefficients 4, 1, and 5. 5 is just a constant on the other side. 2, 1, and 5, right? Okay. So notice that as we transfer these coefficients here, what we've created a column of numbers which are the coefficients of variable x in two different equations. In the second column, these numbers are the coefficients of variable y in two different equations, and the far right numbers are the constant values that we have. Okay, so let's do the same thing for a system of 3 equations and 3 unknowns. So we want to write the augmented matrix once more. For this system, we have 3x minus z equals 12, y equals 6, 2x minus 5y plus z equals 19, right? Okay, so here Notice that we have 3 variables overall in the entire system, to x, y, and z, but not every equation has all the variables. Now for those equations, we cannot skip the coefficient. We have to enter 0 for it. So let's do that. So for the first equation, we have an x, so 3 is the coefficient. There is no y, so we enter 0. There is a z, and the coefficient of that is -1. And finally, the right-hand side is 12. The second row, there is no x, so we enter 0. There is a y, so we enter 1, right? That's the coefficient of variable y in the second equation. There is no z, so we enter 0 again, and then 6 will be the number on the far right-hand side. The bottom row, we have 2 as the coefficient. We have all 3 variables, that's good. And then we have -5. We have 1, and then we have 19. So that's the augmented matrix for this initial system. Now, the method of Gauss-Jordan, or elementary row operations, begins with an augmented matrix, the one we just talked about. So before we get more details on this method, let me draw a diagram. Suppose, and this diagram is a big picture of how the Gauss-Jordan and the different pieces of it work. This is just a big picture. It doesn't have details. So I want to use the analogy of riding a bus. Suppose we want to ride a bus from UNLV to somewhere on Maryland Parkway. Let's say we want to go to, let's say this is the Target store, which is right after Flamingo, as you ride the bus northbound. And then we can get off the bus on this side of Flamingo. So here is Flamingo right here on that. Right, that's Flamingo. So let me Flamingo, right? We can either get off the bus on this side or get off the bus on that side, right? On that side of Maryland Parkway. So this on that side, and this is Maryland Parkway, right? Okay, so if we get off on the bus on this side, it's fine, but we got to do a little bit of more walking to get to the store. If we get off the bus on this side, it's much less walk, but we had to ride the bus through this intersection, right? So now, in the subject that we're about to talk about, this station is called the row echelon matrix. That's the name of that destination. And that destination is reduced row echelon matrix. So the reason I'm using this analogy is that I want you to know that both of these matrices will get you to where you want to go and solve the system. But the row echelon matrix, you got to do a little more work. If you stop here, you got to do a little more work to get to your destination, whereas the reduced row echelon matrix, if you ride the bus that much, then you're right there. You're right at the solution point. Which one is better? There's no better or worse here, but if you look at this subject, mathematics, reduced row echelon form has much more or many more applications than the row echelon matrix. So I would prefer this because it has more applications. It has more uses than the row echelon form. But we'll talk about both so that you're familiar with both, especially when you complete the online homework, you'll need that. Okay, So let's see at this point, don't worry about how we get from this point to each of these matrices. Just I want to make sure that you know how each of these forms look and how you can use it to solve a matrix. That's my goal now. And then after you're familiar with how they look and how you can use it to solve the system, then we can talk about the details of how to get each one of these matrices. Okay, so the question is, okay, so suppose we use this matrix, suppose we use this as an example. Suppose this is our augmented matrix, right? Then we do our elementary row operations, which we will not talk about now, but we will talk about in a few minutes. We apply the elementary row operations, and we get to this point. We get this matrix. The important characteristics of this matrix, I'm going to use with red pen to highlight those. Okay, so this is a row echelon matrix. Notice the look, how it looks visually. You have the diagonals that are 1. Beneath the diagonal, you have a 0. And above it, there are all kinds of numbers. These numbers can be anything. But the diagonals must be 1, and any number below it should be 0. If you have that, you have a row echelon matrix. And you can stop there and solve the system using this. So how do we solve the system using the row echelon form? Well, notice that, or remember that, each of these columns are the coefficients of variables, right? The first column, these are the coefficients of variable x. The second column are the coefficients of variable y, and the far right numbers are the constants. So knowing that, start from bottom up and rewrite the original equation with the variables included. So using that row, we can say that 0 times x is just 0, so no need to write it. 1 times y is y, and then equals the constant, which is 3. So looking at the bottom row, we already know what the value of one of the variables is. It's y equals 3. Okay, so we already have that. Now let's move up and rewrite using these numbers in the row echelon matrix. We're going to rewrite the full equation. So we're going to write 1 times x is x, minus 2 times y is minus 2y, equals the constant, right? So I'm rewriting the original equation with the variables attached. Now we've already figured out what y is, so we can plug that in here and solve for x. So x equals minus 2 times 3 equals 2, x minus 6 equals 2, and x equals 8, right? So we have x, we have y, and we can put these two together and get 8 comma 3 as the solution of that system. Now we were able to do this to solve the system using the row echelon matrix. Okay, so that's one of the destinations at which we can stop and solve the system, the row echelon. So now let's do the same thing with a 3 by 3 matrix. Okay, so suppose we have this augmented matrix. Okay, we don't have to include a vertical line, but it's okay. A vertical line separates the coefficients of the variables from the constant column of constants. Okay, so after we implement the elementary row operations, we get this row echelon form. Again, make sure you understand the row echelon form visually. Okay, so I'm going to use red ink to highlight what's important in a row echelon matrix, or what makes it a row echelon matrix is shown in red ink, basically. Like that. So once again, notice the characteristics of the row echelon matrix. All the diagonals are 1. Numbers below it are 0. The numbers above the diagonal ones can be anything. So that's a row echelon matrix. So I'm going to write underneath this. This is row echelon matrix. Okay. Now, how do we use this to solve this original system? And whenever I talk about this in class, there's always people asking me, well, how do you get this from here? We will talk about that. We haven't yet talked about that yet. We will. But I want to make sure that you know what a row echelon matrix looks like and how to use it to solve the original system. And we will talk about these row operations plenty of times. So, once again, please remember, each of these columns represents the coefficients of a variable. So the first column, I mentioned x, y, z before, so let's give these another label. Let's call these x1, x2, x3, and these are the constants. The column on the right, those are just constants. I'm labeling these variables like this because you're going to see x1, x2, x3 a lot, so it's better to get used to those kinds of variables early on. Okay, so once again, we start from bottom up. With these numbers, write the original equation. So 0 times x1 is just 0. 0 times x2 is 0. 1 times x3 is x3 equals 1, right? So we already know what x3 is. Just look at the bottom row, and that'll tell you, right? The x1 and x2 drop out because they have coefficients 0. The coefficient of x3 is 1. 1 times x3 is x3 equals 1. Great. Now, let's move one row up again. And let's use these numbers to write an equation. These numbers, let's use them to write our equation. Is there going to be an x1 in this equation? No. The reason is 0 times x1, the coefficient of x1 in this row is 0. So x1 drops out. 1 times x2, yes, we can write that down. Minus 12 times x3, we can write that. Equals the far right, which is a constant, negative 15. Okay, we already know that x3 is 1. We can plug it in here and solve for x2. So let's do that. x2 minus 12 times 1 equals minus 15. Then we have x2 minus 12 equals minus 15. x2 equals minus 15 plus 12, right? Move this to the other side, it becomes positive. So x2 is equal to minus 3. So we got that. We've got x3, we've got x2, now x1. How do we find x1? Well, we move one row up. So let's come here. We're going to write the full equation with the variables attached using these numbers in the top row. So 1 times x1 is x1. Minus 1 times x2, minus x2. 1 times x3 is equal to x3. And 8 is the constant on the other side. Right? Okay, great. So now we know what x3 is. We know what x2 is. So let's plug it in and then solve for x1. So x1 minus x2, that's minus 3, plus x3, which is 1, should be equal to 8. So this is positive 3 plus 1, that's 4, equals 8. So x1 equals 4, right? 8 minus 4, if you move 4 to the other side, it becomes negative. Subtracted from 8, you get 4. So there's x1. Okay, so now, using the row echelon form of a matrix, we have been able to solve the system, which is, so if we have x1, comma, x2, comma, x3, that is equal to 4, comma, negative 3, comma, 1. That's the solution of the system. Okay, so now we've talked about how to use the row echelon form to solve a system. Let's talk about how to use the reduced row echelon form. We haven't talked about that yet, right? So we'll do that now. So here's the next question for us to answer. What is a reduced row echelon form of a matrix, and how can we use, or how does it help us to solve a system? Okay, that's the question before us. Well, now let's take that same matrix that same augmented matrix that we used in the previous example for row echelon form. We're going to use the same augmented matrix, but this time we're going to write down the reduced row echelon form for it. So here's that example. We had 1, negative 1, 1, 8, and 2, 3, negative 1, negative 2, 3, negative 2, negative 9, and 9. Okay, and if you prefer, we can put the vertical line here to divide the coefficients of the variables from the constant values, which are in the far right column, always. Okay, so after row operations, and we will talk about that next, we're going to find remember the analogy that I used as row echelon form and reduced row echelon form being different stops along the same route? So whatever we were doing in our row operations is the same to get to these two destinations, but with reduced row echelon form, we go a little bit further. And here is the reduced row echelon form. So the red ink shows you the dominant characteristic of a reduced row echelon form, which is all the diagonals are 1, numbers below it are 0, numbers above it but before this vertical line are 0, and the only the numbers on in the right hand side column can be anything. These are actually the solutions of the system. But once we get the augmented matrix to this point, so this is our augmented matrix. And this is our reduced row echelon form, we can easily solve the system, because please remember that each of these columns represents the coefficients of the same variable in 3 different equations. So these are the coefficients of, let's say, x1 in 3 different equations. These are the coefficients of variable x2 in 3 different equations. And these numbers are the coefficients of variable x3 in 3 different equations. Okay, great. So now we don't have to, with this one, we don't have to start from the bottom. We can start anywhere, because x1 has coefficient 1, so 1 times x1, and those 2 variables drop out because they have coefficient 0. So coefficient of x1 is 1. 1 times x1 is just x1 equals 4. Okay, so x1 equals 4. x2, in the second row, x2 has coefficient 1. The other 2 variables have coefficient 0, so they drop out. So x2 equals -3. And x3 is equal to 1. So we can put it together, 4, -3, 1, which is the final solution we got with the row echelon form, which we discussed before this. So now you're familiar with both row echelon form and reduced row echelon form, and you know how to use those matrices to solve a system. Now, of course, the question is, how do we get to the reduced row echelon form? The row echelon form, you probably will see it in your online homework, but on the exams, you can use any of these methods to get the final answer. Unless the question, of course, specifies. If the question leaves it open, if it says solve this system and it doesn't specify what method to use, then you'll use the method that you're most comfortable with. But if a question says solve the system using the Gauss-Jordan method, then you have to use this. Or if the question says use the elementary row operations, which is the same thing, Gauss-Jordan, to solve the system, then you'll use this. You'll have to use this. Otherwise, you can use the other method, elimination method, which we discussed in the previous section. So please read questions carefully. Let's see what method it's asking you to use. If it's open, if it's left open, then you can use any method that you prefer. Okay, so now let's talk about elementary row operations. So here's the question: what are the elementary row operations? And let me add, this is critical. at the end here, preferred. If you comb through the internet, if you watch enough videos, you'll see that there are lots of different row operations. I don't want, because we're introducing this topic, I don't want you to use those other operations that you might find on the internet or somewhere in the YouTube clips. A lot of those methods are valid, but they take significant amount of skill and facility with this method. Because you're just learning this, you don't want to use those because it'll give you trouble. It'll probably won't get you the right answer. It's like driving a regular car and all of a sudden attempting a Formula One car, right? You need to have a little bit of training, a little bit of more exposure with this material before you can use these other methods. For the purposes of this course, and because we're just introducing this to you, then these are the row operations that I want you guys to use. Okay, so one of the row operations is we are allowed to interchange any rows in the matrix. So you can interchange row 1 with row 2, row 2 with row 3, row 3 with row 1, and so on and so forth. Of course, you have to have a good reason for doing this. Otherwise, interchanging the rows is not going to achieve anything. So that's one of the row operations we are allowed to use. The other one is we can multiply the pivot row, and we'll talk about what this pivot row is, the pivot row by an integer. We can do that. And we will get to that, why this is a necessary operation sometimes. And then we can multiply a row, or any row, by a constant. Well, multiply the pivot row by, I said, in an integer. Sometimes you might multiply the pivot row by a fraction, say 1/2. So let me correct myself with this thick pen and say multiply the pivot row by a constant. That's a better word. By a constant, because it's not always an integer. It can be any constant. And then multiply any row by a constant and add it to the row we are changing. So notice here, I wrote this add in red ink because we do not want to subtract. So can you subtract rows to get the numbers you want? Yes, you can. But it causes a lot of trouble for many of you. So I don't want you to subtract. I want you to stay safe and get the correct answer. Subtraction causes a lot of problem because it's a lot of distribution of the negative symbol into many numbers. So let's stay away from subtraction and just add one row to the next. Okay? So these are the main row operations for us to use. We can interchange any rows in the matrix. We can multiply the pivot row by a constant. We can do that, and we'll get to the reason why we can. This is a good operation for us. Or we can multiply any row. Actually, any row, let me also, instead of any row, let me also use pivot. pivot row. Multiply the pivot row by a constant and add it to the row we are changing. I think that better describes what we're going to be doing in this course. So again, these three row operations are not the only valid ones, but these are the ones that I like you to use because you are just a beginner in this method. Okay, having talked about that, let's solve examples using this Gauss-Jordan method. So we want to use the Gauss-Jordan method. I'll quickly add in parentheses, i.e. the elementary row operations. Use that to solve the following system. And we're going to start with a smaller system, a system of two equations and two unknowns. So we have 4x plus y equals 5, and then 2x plus y equals 5. Okay, so the beginning of the Gauss-Jordan method starts with the augmented matrix. So let's write down the augmented matrix for this. So 4, 1, 5, and then 2, 1, and 5, right? This is the augmented matrix for that system. Now, remember the reduced row echelon form? Let me write it down here. So here is 1, 0, 0, 1, and then. So the reduced row echelon form of a matrix for this system of two equations, two unknowns, is going to look like that. When we're done, this is going to look like that. Now compared with that, the method works like this. We're going to go from this matrix to that matrix, column by column. Now, some of you might be thinking, well, the method is called row operations. How come we go column by column? Well, I agree with you. This is probably one of the misnomers in mathematics, that even though it's called elementary row operations, what we're doing really is sweeping column to column from left to right. So our objective is to make this column look like this column. Once we're done with that, we move to the second column and we make that look like this second column. Having said that, it's critical that you remember when you obtain each column to match that, the first thing you obtain is the 1. In that column, the first thing you need to obtain is 1. Then you worry about the 0 in that column. And once you're done with the first column, you move to the second column. The first number to obtain is the 1. Then you worry about obtaining the 0. I'm talking about going from here to here. Let me say this once more, just to be sure. In going from the augmented matrix to the reduced row echelon form, and I'm going to label these. So this is augmented matrix, and this is reduced row echelon matrix. In going from here to here, we obtain this column by column. So first we need to figure out, obtain this column to go from 4, 2 to 1, 0. Once we've done that, then we go from going from this column to that column to obtaining 1, 0, and 1. Having said that, in each column, the number to obtain first or convert first is the 1. So right now I'm looking at this. where I would begin in the first column is to go from 4 to 1. The 1 in each column is obtained first. Then we worry about the zeros in that column. Okay, having said that, what would be the row operation to go from 4 to 1? Well, this is the first row. This first number, this 4, is in the first column. We can multiply this whole row by 1 over 4. So let's do that. So this is the row operation. Row 1 is equal to 1 over 4 times row 1. And which row operation I'm using? Let me scroll up. I'm using that one. Multiply the pivot row by constant. That's what I'm doing. Row 1 is equal to 1/4 times row 1. Why are we doing this? Because we're going to obtain the 1. Okay, let's do that. We're going to carry out this row operation. So 1/4 times 4 is 1. 1/4 times 1 is 1 over 4. 1/4 times 5, 5 over 4. And the second row stays the same. 2, 1, 5. Okay, so compare this with this, which is the reduced row echelon form. We got the 1. Now we need, in the second, we can't go to this column. We're not done with the first column. Look at it. We still have to convert the 2 to 0. So at this point, as soon as you get this 1, as soon as you get any of these 1s, that row, the row that contains the 1, is the pivot row. Let me repeat that. As soon as you obtain any of these 1s in each column, the row that contains the 1 becomes the pivot row. Why is that important? It's important because you're going to need to use the pivot row to obtain the 0 in the other spots in the same column. You have to use the pivot row in this method. Okay, so that means row 1 is the pivot row, because we just got the 1 for it, right? The 1 in that column is in first row, so that makes this row pivot row. That means to convert the 2 to 0, I need to use the pivot row to achieve that. So let's do that. So we're changing row 2, because the 2 has to be 0, right? And the 2 is in second row. So row 2 equals, all we need is add a -2 to this, and we're going to get a 0. But where is the -2 going to come from? It's going to come from multiplying the first row by -2, -2 times row 1, and then add it to row 2. So this row operation will give us a 0 in that spot. And let me write down the matrix for that, for this row operation. All right? So actually at this point, it's a good idea for you to pause the video, write the next matrix down on your own. If you're not confident, it's totally okay, but it's important that you build up your own skill in solving these problems. So pause the video and write down the next matrix, and then come back to the video and see what I have and compare it with your solution. Okay, so notice the first row. I'm assuming you've done that and you're back and you already have your solution in front of you. The first row isn't changing, so I'm going to write it down as it is because that's our pivot row, right? Now, the second row is changing according to this row operation. -2 times 1 plus 2, 0. -2 times 1/4, that's -1/2 after simplifying. -1/2 plus +1 is +1/2. -2 times 5 over 4, that's -10 over 4. -10 over 4 we can simplify it, right? It will be minus 5 over 2. Then minus 5 over 2 plus 5. So this is minus 2.5. Minus 2.5 plus 5, it's positive 2.5 or positive 5 halves. Like that. If you don't want to do that, you can simply minus twice this is minus 10 over 4. Simplify it to minus 5 over 2. Then add it to 5. So minus 5 over half plus, or 5 over 2 plus 5. The common denominator is 2. So then we have negative 5. And the 5 here has denominator 1. So we have to multiply it by 5 over 5, which means plus 25. So we get 20, no, so let's see, minus 5 over 2 plus 5, and then, so this is 10, sorry. This is 10, so this would be times 2 over 2, 2 over 2. To get the common denominator for 5, we have to multiply the 5 and its denominator, which is 1, by 2 over 2. So we get minus 5 plus 10 over 2, which is 5 over 2, which is the same thing here. Okay, so now we have this matrix. Compare this with the reduced row echelon form, which is 1, 0, 0, 1, and then we have these numbers will tell us the solution of the system, right? Compare this with that. Do we have the first column? Yes, it's done, right? Compare this with that. That column is done, and we're sweeping column to column. Now, we need to move to the second column to get it to look like this. As I said, you want to start with you have to get the 1 first before you worry about the 0. You do not want to start with the 0. So first get the 1. Once you have that, then worry about the 0. How do we get the 1? Well, we can easily do that by multiplying the second row by 2. So row 2 equals twice row 2. That's the row operation for that. Okay, so let's write down the new matrix here. The first row isn't changing, so 1, 1/4, 5 over 4, and then multiply the second row by 2, 0, 1, and then 5, right? If you multiply this row by 2, these are the numbers you get. So now, compare this with this matrix. Did we get the 1? Yes, we did. Now we're going to worry about the 0. We're going to need to convert the 1/4 to 0. How do we do that? Using the pivot row. What row is the pivot row now? The second row. Why? Because we just got the diagonal 1 for it, the diagonal 1s. As soon as you get the diagonal 1 for any row, that row becomes the pivot row, which is important for you to remember because it means you're going to have to use that row, the pivot row, to get the zeros in the other spots in the column. So that means to get this 4 to be 0, I'm going to have to use the pivot row, which is the second row. Okay, so what is the row operation for doing that? Well, all we need is to add a negative 1 over 4 to this, and we're going to get a 0 in that spot. Okay, great, but where does the negative 1 over 4 come from? Well, it comes from multiplying the pivot row by negative 1 over 4, and then adding it to the first row. So row 1 equals. Row 1 equals because we're going to change row 1. That's the main purpose of this row operations. We're going to change row 1. So row 1 is equal to minus 1/4 row 2, which is the pivot row. Multiply the pivot row by minus 1 over 4, and then add it to row 1, like that. Now it's a good point for you to pause the video, carry out this row operation, obtain the next matrix, then come back to the video and see if your answer, your next matrix, matches the next matrix that I'm about to write down. Okay, so please do that. All right. So I'm assuming you've done that, and now you're ready to see what I have. So minus 1/4 times 0 is 0, plus 1, 1. Minus 1/4 times row 2, which is 1 at this point, that's minus 1/4, plus 1/4, that's 0. Minus 1/4 times 5 is minus 5/4, added to plus 5/4, it's 0. And then the second row, we can write it as it is, and compare that because it's off the screen. Let me write it here again. So this is the reduced row echelon form, right? Compare what you have. Compare this with this. Are we done? Yes, we're done, because the left side is the reduced row echelon form, so the other side is going to be the solution. So how are we going to write down the solution? Well, just remember that the first column, these are the coefficients of variable x in this system. The second column are the coefficients of variable y, and then so we can say x equals 0. Y drops out, right? In the first row, y drops out because it has a coefficient 0. So there is no y. So x is equal to 0, which is that constant. In the second row, there is no x because its coefficient is 0. So 0 times x is 0. We're not going to write it down. 1 times y is y equals the constant here, which is 5. So the solution of the system is 0, 5. Okay, and I trust that you will write down your questions on the discussion board for this. Let's do another example. This time we're going to use, the example will be using 3 equations with 3 unknowns. So it's going to be a bit bigger matrix. Or let me just say Gauss-Jordan. That's better. Gauss-Jordan method, i.e. Elementary row operations. Okay, and here's the system we're going to solve. I strongly urge you and encourage you to, at this point, pause the video, solve the whole thing at once on your own, and then come back to the video and see how I'm approaching the solution. Okay, so I'm assuming you've done that and you're back. And the first thing I would do, the Gauss-Jordan method or elementary row operations, it starts with the augmented matrix, right? So let's write down the augmented matrix for this system. 2, -1, 1, and the constants on the other side. Then 1, 1, 1, 5, 1, 2, -1, and 3, right? Just remember, these are the coefficients of variable x, these are the coefficients of variable y, and these are the coefficients of variable z, and these are the constants. Some authors, when you read textbooks, some authors like to put this vertical here, some don't. So it's not an error if you leave it out. I like to use it because it's a visual aid. It helps me keep track of, okay, all these numbers are the coefficients of the variables, all these numbers are constants on the other side of the equality symbol. All right, so our objective is to get this augmented matrix to be to convert to a reduced row echelon form matrix, right? In other words, this is where we're going. This is our destination. Like that, right? We'd like to go from here to here. Just think of it as that bus ride. Now, as we did in the previous example, we're going to do this column by column. So, looking at this, which number would you obtain first? Would you obtain the zeros or the 1? If you remember what I said, you would obtain a 1 in that corner. So that's the one that's the number you want to obtain first. Now there are options for you here. You can multiply this whole row by 1 over 2, right? That's a valid approach. But that approach has a consequence of producing fractions here. Do you want that? Well, it's okay if we don't have it. It's okay if we have it, but we prefer not to have fractions, right? As much as possible, because they waste our time working with them. So let me bring back those list of row operations that I gave you. So among these three, think about which one would you use at this point, right? If you pick number 1, that's a wise choice because that helps you get a 1 in that corner, and at the same time, it'll help you avoid generating any fractions. So let's interchange row 1 and row 2 in order to get a 1 in that corner. And remember, we're focusing on this column now, for now. Right? So let's do that. We will interchange row 1 with, I'm going to put a double-headed arrow here to indicate interchanging of rows, row 1 with row 2. Okay, so the resultant matrix will be as follows. We will have 1, 1, 1, and 5. Then 2, negative 1, 1, 2. And the third row stays where it was, right? Like that. Okay, now compare this with the reduced row echelon form. We're not done with column 1, right? We have more work to do. We've just gotten the diagonal one for the first column. So which row is the pivot row now? That's important for you to establish, because in order to change the 2 and 1 to 0, you're going to have to use the pivot row. Well, we just got the 1 in that corner, so our first row is going to be the pivot row in the upcoming row operations. All right, so now we have to convert the 2 to 0 and the 1 to 0. Great. So these are the 2 row operations for doing that. If you haven't paused the video yet, please pause the video, write down the row operations on your own, then come back to the video and see what I'm doing. So I'm assuming you've already done that and you're back, and here are the 2 row operations we need to have to convert the 2 and 1 to 0. So row 2, that's where the 2 is, equals, all we need is add a negative 2 to this 2 to get a 0. But where does the negative 2 come from? It can come from by multiplying the pivot row by minus 2 and adding it to this 2. So minus twice row 1, which is the pivot row, plus row 2. All right, so now we need to get this 1 to become 0 as well. Well, all we need is to add a -1 to this. But where does the -1 come from? It comes from multiplying the pivot row by -1 and then adding it to this one. So let's write the row operation for that. This one is in row 3. So negative -1 times row 1 plus row 3. So these are the two row operations we need. Now that you know the row operations, I strongly recommend you to pause the video, use these to write down the next matrix. Once you're done, come back to the video and see what I have. Okay? So I'm assuming that you've done that and you're ready to see my solution here. 1, 1, 5. I'm going to do this row operation first. Minus twice row 1 plus row 2. Minus 2 times 1 is -2. Plus 2, 0. Minus 2 times 1 is -2. Plus -1, -3. Minus 2 times 1 is -2. Plus 1, -1. Minus 2 times 5 is -10. Plus 2, it's -8. Okay, now let's do this row operation. This one says multiply row 1 by -1 and add it to row 3. So -1 times 1 is -1, plus 1, 0. -1 times 1 is -1, plus +2, 1. -1 times 1 is -1, plus -1, that's -2. -1 times 5 is -5, plus 3, -2. Now compare this result with this, the reduced row echelon form. Compare this with this. Are we done with the first column? Yes, we're done, right? This looks like that, so we're done with the first column. Now we move to the second column, this one. Now we need to convert this column to look like that. So there are two row operations available to us in this case. For one thing, we can multiply the second row by -1/3, right? If you multiply this row by -1/3, it'll give you a 1 in that spot, which is what you want. That's a perfect valid solution. But at the same time, that will generate two fractions here, which is fine if we cannot avoid it. But if there's a way to avoid that, why not, right? So, can we interchange, because all we need is a 1 there, and we don't want to destroy this 0 or this column that we just got. Having that in mind, can we interchange row 2 and row 3 to get a 1 there? We can. In this is very lucky because not only we can get a 1 in there by interchanging these two rows, row 2 and row 3, we're not going to destroy the 0 that we got, because sometimes you might have a non-zero number. I mean, in this case, sometimes you might not have a 1 here. In this case, you have a 1 here, and you have zeros here naturally, since you're in second column. So it's okay to interchange rows 2 and 3. So let's do that. So we're going to change row 2, or interchange row 2 and row 3. That's going to give us this matrix. Row 1 isn't changing, right? So now 0, 1, -2, -2, and then bring the second row down to row 3. So 0, -3, -1, -8. Right? And we got it. We got the 1 in the second column. Remember, please, that in each column, you get the 1 first, then you worry about the zeros. Okay, now we need to convert the 1 and -3 to zeros, right? So my question to you now is, which row is the pivot row at this point? Did you answer it in your own head? Okay, great. So if you answered row 2, that's correct. Row 2 is the pivot row. Why? Because we just got the 1. With interchanging the rows, we were able to get the diagonal 1. So the second row becomes the second row which contains the diagonal 1, it becomes the pivot row. So this is our pivot row. It's important because now we know in the next row operations, we're going to have to use the second row to convert the 1 and -3 to zeros like that. Okay? So let's write down those 2 row operations. So to change this one to 0, we're changing row 1, right? That 1 is in row 1, equals, all we need is to add a -1 to this to get it to be 0. So where is the -1 going to come from? We can multiply the pivot row by -1 and add it to that. So minus row 2 plus row 1. So for this -3, that's in row 3, right? So we're going to have to change row 3 equals. All we need is a +3 to be added to this -3 so that we can get a 0. But where can we get the +3? Easily, we can get the +3 by multiplying the pivot row by 3 and adding it to row 3. So 3 times row 2, which is the pivot row, plus row 3. Okay, so now it would be a good point for you to pause the video, using these row operations, write down the next matrix, then come back to the video and compare your work with what I'm going to write down. Okay, I'm assuming you've done that. Great. So we're going to use this row operation first. So this is saying multiply row 2, which is the pivot row, by -1 and add it to row 1. So -1 times 0, 0, plus 1, 1. -1 times 1 is -1, plus 1, 0. -1 times -2, +2, plus 1, 3. -1 times -2, +2, plus 5, 7. So the second row is our pivot row, so it does not change. So 0, 1, -2, and -2. Now the second row operation is going to change row 3. How? This way. 3 times row 2 plus row 3. So 3 times 0 is 0 plus 0, 0. 3 times 1 is 3 plus -3, 0. 3 times -2, that's -6. Plus -1, -7. 3 times -2, that's -6. Plus -8, -14. Okay, I hope that makes sense. All right. So now, compare this matrix that we have now with the reduced row echelon form, which is our objective, right? Our objective is to get this to be that. Are we done with the second column? Yes, right? The second column, we already got 0, 1, 0, 0, 1, 0. And the first column is 1, 0, 0, 1, 0, 0. So now we can focus on the third column. So please remember, in each column, the first number that you convert is the 1 to 1. That's the one you want to get first, and then you worry about the zeros. Well, think about how we can get a 1 instead of -7 in this spot, right? If I bring the row operations, see, let me bring back this slide that has the row operations on it. Which one of these would you use? If you answered the second one, perfect. That's the correct one. multiply the pivot row by a constant. It's going to be our pivot row, this one, because we're going to get the diagonal 1 for it pretty soon. So we can multiply it by a constant and get a 1 there. What constant would that be? It would be minus 1 over 7. So multiply row 3 by minus 1 over 7. And we're going to get a 1 in that corner, which is what we want, right? Okay, let's do that. That means the first 2 rows are not changing. Oh, I'm sorry. So let me correct that. So this would be 1, right? And then minus 1/7 times minus 14th, times minus 1/7, it'll be positive 2. So this will be 2. Like that. Sorry about that error. Okay, so now we have to focus on obtaining the zeros, right? We are not done. We got to convert the -2 and 3 to zeros that we need. All right, so the pivot row, which row is the pivot row now? If you answered row 3, you are correct, right? This is the pivot row. And we're going to use the pivot row to get the zeros that we need, using the row operations, right? So to get the 3 to become 0, all we need is to be able to add a -3 to it. Where is the -3 coming from? Well, we can multiply the pivot row by -3 and add it to that. So row 1, we're changing row 1, so row 1 equals -3 times the pivot row, which is row 3, plus row 1, which is the row we're changing. So that's the row operation for getting a 0 instead of 3. To getting a 0 in this spot, all we need is to add a 2 to this -2 to get 0, right? Where is the 2 coming from? Well, it's going to come from multiplying the pivot row by a +2 and adding it to this -2. So -2 is in the second row, right? So row 2 is equal to twice the pivot row, which is row 3, plus row 2, which is the row we're changing. Okay, so let's write down the next matrix. I hope you repeatedly pause the video, write down your own solution, and come back to the video to see how you're progressing through this procedure. All right, so first, carrying out this row operation, this is saying multiply row 3 by -3 and add it to row 1. Great, so -3 times 0 is 0 plus 1, 1. -3 times 0 is 0 plus 0, 0. -3 times 1 is -3 plus 3, 0. -3 times 2 is -6 plus 7, 1. Then this row operation, this is saying multiply row 3 by 2 and then add it to row 2. So twice 0 is 0 plus 0, 0. Twice 0 is 0 plus 1 is 1. Twice 1 is 2 times 1 is 2 plus -2, 0. 2 times 2 is 4 plus -2 is +2, and row 3 is the pivot row and it's not changing, so we're going to write it down as it is, 0, 0, 1, 2. So compare this matrix with the reduced row echelon matrix that we've been after ever since we started this procedure. Compare this with that. The left-hand side is exactly like that. So are we done? Yes, we are done, and now we can write down the answer to this problem. So just remember that these columns are the coefficients of variable x. these columns, or this column, these numbers are the coefficients of variable y, and this column, these are the coefficients of variable z. So in the first row, y and z have coefficients 0, so they drop out. So x equals 1. 1 times x is x equals 1. In the second row, y has a coefficient 1. X and z have coefficient 0. So 1 times y is y equals 2. Z in the third row, the z has a coefficient 1, but x and y have coefficients 0, so they drop out. So 1 times z is z equals to 2. So the solution of the system is 1, 2, 2, and that's the point at which those three initial lines intersect, or they are equal to each other at that point. Okay, I hope what we discussed today in this section makes sense. If not, please let me know with your questions. And thank you for persisting through these videos, and that will help both of us to create a successful class for all of you. So for now, I bid you goodbye and have a nice day until next time.